Welcome back to the deep dive. Today, we're stepping away from the flashy side of programming for a minute.
Right. No fancy UIs, no big AI algorithms.
None of it. We're going to talk about something way more fundamental. We're talking about digital memory.
Which is funny because without this so-called memory, all that flashy stuff is, well, it's temporary. It's gone the second you turn the power off.
That is the thing, isn't it? I think when people imagine computing, they think of the processor, the brain.
The thinking part.
Yeah, the thinking. But if you can't make a thought permanent, you don't have a computer. You just have a really, really expensive calculator.
A very fleeting one.
So today we are unpacking Chapter 7, File Handling. And I know, that title sounds a little like office admin work.
It does sound a bit dry.
But the source material paints this picture of something so much grander. It's about how we stop data from just vanishing into the ether.
It's the anchor. I mean, if you look at the history of computing, the ability to calculate was step one. But the ability to store, to create a file that exists after the program is gone.
That was the game changer.
That was the moment computing became, you could say, civilization building. We're moving from volatile RAM to non-volatile storage.
And the sources use this great visual metaphor, the digital archive.
I like that one.
It's like you picture these endless rows of old metal filing cabinets, and then they slowly transform into modern server racks.
Yeah.
And that's our mission today, to understand the mechanics of that archive. We're not just talking about hitting save. We're talking about the hierarchy of data, the algorithms for merging and reporting.
And the architecture that keeps a massive banking system from just completely falling over.
Exactly. And what's interesting is we're going to see that whether you're coding in Python, C++ yet, or Java, the underlying logic is universal.
Totally. The syntax changes, but the strategy for handling data, it hasn't really changed all that much in 50 years.
So let's start at the most basic level. The sources make a really big deal out of the distinction between different types of files. For most of us, I think a file is a file. You double-click it, the OS figures it out. But under the hood, there's this really hard line drawn between text files and binary files.
There is, and it all comes down to interpretation. You have to remember, on the disk itself, everything is just ones and zeros. It's all binary.
Right.
The difference is how we, or rather the programs, agree to read it.
So when I open a .txt file or a .csv file, I see English, I see numbers, but we've all done this, right? You try to force open an application and a .exe or a .jpg image inside a text editor.
And it looks like complete chaos.
Alien hieroglyphics, just a wall of strange symbols.
And that chaos is basically a translation error. A text file is built on a very simple agreement. Each byte maps to a character table, like ASCII or Unicode.
Okay.
The software expects letters, numbers, punctuation. But a binary file, like an image or an MP3, doesn't follow those rules at all. Its bits represent pixel colors or audio frequencies or CPU instructions.
So the text editor is desperately trying to translate the concept of bright red into the letter Z or something.
Exactly. And that's why you get garbage. Text files are for us. For humans, they're portable. Binary files are for the machine. They're dense, they're fast, but you need the right key to decode them.
That makes sense. And that distinction kind of frames everything else. But before we get to actually working with files, the material outlines this data hierarchy.
The building blocks of information.
Yeah, we start with characters, the atoms, A, 9, whatever. Then those build into fields, which build into records, then files, and then the whole database.
Like a set of nesting dolls.
It is, but it feels very rigid. I mean, in today's world, we're all about unstructured data lakes, just dumping everything into a big pile. Does this old school hierarchy still matter?
I would argue it matters more than ever, because even in a messy JSON file or a social media post, you still have these units. You can't escape it. A field is just a meaningful name for a bunch of characters. The word Alice is just 4 letters until you put in a field called name.
So the hierarchy is really about how we create meaning out of the noise.
Precisely. You group related fields, name, ID, salary, and poof, you have a record. That record describes one person, one thing. You group those records, you get a file. The computer needs that structure to know where one thought ends and the next begins.
Okay, so we have our structure, we have our file types. Now let's talk about the actual workflow. The source material lays out this 4-step procedure for any code that touches a file.
The 4 pillars: declaration, opening, processing, and closing.
Right. And most of that is pretty straightforward, but I want to focus on opening and closing for a second. When a program opens a file, what is actually happening there?
It's a handshake. Your program is basically asking the operating system for permission.
May I please read the...
Exactly. Hey, OS, I'd like to access this spot on the hard drive. And if the OS says yes, it gives you back a handle. Think of it like a direct phone line to that data, and this is where you have to state your intentions.
That's the R and W modes I saw in the code examples.
Right. R for read, W for write. And it seems like a small detail, but it's a critical safety feature. If you open a file in read mode, the OS will physically prevent you from accidentally deleting it.
Okay.
But if you open it in write mode, you're telling the OS, hey, I might be about to overwrite this whole thing. Which is a very powerful and dangerous thing to do.
And that brings us to the part that every new programmer seems to forget. Closing the file. Step 4.
The sources are so emphatic about this. Why is it such a huge deal? If my program is done, doesn't the computer just clean up?
You'd think so. And sometimes you get lucky. But relying on luck is not great engineering. The key reason this matters is something called the buffer.
The waiting room.
The waiting room, that's a perfect analogy. Think about the speed difference. Your CPU is a Ferrari. It does billions of things a second. Your hard drive, even a new SSD, is like a bicycle in comparison.
Okay, so a huge mismatch.
Massive.
Yeah.
If the CPU tried to write to the disk every single time you typed one character in a document, your entire system would grind to a halt.
So it cheats. It optimizes. It collects your changes in a super fast piece of RAM, this buffer, this holding area. It waits until it has a nice big efficient chunk of data, and then it writes it to the slow bicycle all at once.
Ah, I see the trap now. If the program crashes or the power goes out before that buffer gets written,
The data never made it. It's still in the Ferrari's passenger seat when the car hits a wall.
gone forever.
Exactly. The close command is what forces that write. It's the instruction that says, hey, flush the buffer. Make sure everything in the waiting room gets saved to the disk right now. It's all about data integrity.
Okay, so close your files, people. It's not just being polite to the computer.
It's necessary. Plus, it gives that handle back to the OS so other programs can use it. It's just good citizenship.
All right, moving from the mechanics to the logic. The source material spends a good amount of time on something called control break logic.
The classic reporting algorithm.
It sounds so intimidating, control break, but when I read the example, a sales report sorted by region, it's really just about noticing when a category changes.
It is.
You've got this list, north, 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 then south, south, and you just want a subtotal for north before you start adding up the south sales.
It sounds incredibly simple to a human brain. You just scan the list with your eyes and you see where the word north stops. But a computer has a major limitation.
It has no peripheral vision.
It's reading the list through a straw. It can only see one line, one record at a time. It has no idea that south is coming up next until it's literally the next thing it reads.
So you have to teach it how to remember what it just saw.
Precisely. You create a variable in memory, let's call it current region, and you store the word north in it. Then for every new line you read, you ask a simple question. Does this new records region match what I'm holding in memory?
And as long as the answer is yes, you just add the sale amount to a running total.
You just keep accumulating. But the instant you read a record that says south, the check fails. South does not equal north, and that is the break.
The control break.
Yes. And at that moment, the program has to sort of panic constructively. It has to pause and say, whoa, stop. Before I deal with this new south record, I need to print the final total for north, then reset my counter back to 0, and then update my memory variable to south.
It's a retroactive summary. It only knows a group is finished because the next one has already begun.
And that leads directly to the classic mistake the source warns about.
The final
group. If the break is triggered by seeing the next different item, what triggers the summary for the very last group in the file?
There is no next item. The file just ends.
And that's why beginners' reports are so often missing the data for the last category. The loop just finishes, and the program never got that mismatch signal to tell it to print the final total. You have to add extra code after the loop to handle that last batch.
It's such a good example of how literal you have to be with a computer.
You have to account for the silence at the end.
Speaking of logic puzzles, let's talk about merging. The scenario is simple. I have two lists, employees from Division A, employees from Division B, and I need one single sorted master list.
One of the most elegant and efficient algorithms in all of computer science. It's the two-finger approach.
But the sources say there are some very strict rules first. You can't just mash any two files together.
No, absolutely not. First, they have to have the same layout, the same structure. You can't merge employee records with sales invoices.
Apples and oranges.
And second, and this is the non-negotiable part, both of the input files must already be sorted by the same key, say by employee ID.
And what happens if they're not sorted?
The whole thing just breaks. The logic completely falls apart. The algorithm's efficiency depends on the fact that it can trust that the very next record in each file is the smallest remaining number in that file.
Okay, so assuming my two files are sorted, walk me through this two-finger idea.
Imagine you have two stacks of numbered index cards on your desk, both sorted from smallest to largest. You put your left index finger on the top card of stack A and your right index finger on the top card of stack B.
Okay, I'm with you.
You just compare the two numbers your fingers are pointing at. Let's say stack A has employee 101 and stack B has employee 102.
101 is smaller.
101 is smaller. So you take that card, you write it to your new master file, and this is the key, you only advance your left finger to the next card in stack A. Your right finger stays put on 102.
I see. So you're in this constant little comparison loop. Now my left finger might be on, say, 105.
Exactly. So now you compare 105 from stack A with 102 from stack B.
102 wins.
102 wins. So you write 102 to the master file, and this time you only advance your right finger. You just keep doing that little dance back and forth, always writing the smaller of the two values.
Until one of the stacks runs out of cards.
Right. And at that point, you know that every remaining card in the other stack is larger than anything you've processed so far. So you can just copy the rest of that stack straight over.
That's really clever. Why is that better than just dumping both files together and then sorting the whole big mess?
It all comes down to efficiency. This is a single-pass algorithm. You only ever have to look at each record one time. If you have two files with 1 million records each, this merge is incredibly fast. Combining them first and then trying to sort a 2 million record file would be way, way more work for the computer.
That efficiency has to matter when you scale up, which is a perfect lead-in to this system architecture section. The sources talk about master files versus transaction files.
This really is a peek behind the curtain of how things like banking have worked for decades.
It feels like it. The problem they're solving is you have this giant critical master file, the bank's database, of every single customer's balance.
It's massive, and it has to be correct.
And then there's me, out in the world, buying a coffee for $5.
Right. And the question is, do you really want the bank to lock down that entire massive critical file, find your specific record, change the number, and then save the whole multi-terabyte file again just for your latte?
That sounds incredibly slow and risky. What if the power goes out while it's rewriting the master file?
You could corrupt the whole thing. Catastrophic failure. So instead, they use a transaction file.
A temporary file.
A temporary log file. It doesn't store balances, it just stores events. It's a simple list that says, user 44 spent $5 at $9 at 2 a.m.
Yeah.
User 99 deposited $100 at 9:03 a.m.
So you're just adding a new line to the end of a small text file.
Which is one of the fastest things a computer can do. It's almost instantaneous. So all day long, these little transactions just pile up in the log, and the huge, important master file remains untouched, safe and sound.
You know, this sounds a lot like event sourcing in modern software design. The idea that your current state is just the result of all the events that have ever happened.
It's the direct ancestor of it. The principle is the same, whether it's a 1980s mainframe or a 2024 microservice. The log is truth. If the system crashes, you haven't lost the data, you've just lost the calculated balance. You can just replay the log.
And then at some point, you have to actually update the master file, right?
That's the batch processing step. Usually late at night, when traffic is low, the bank runs a program that takes that day's transaction log
and merges it into the master file using that two-finger logic we just talked about.
to create a new, updated master for the next day. And that explains why sometimes a charge shows as pending on your bank statement.
Ah, the transaction is in the log, but the batch process hasn't run yet to make it official in the master.
You got it. You sacrifice a tiny bit of real-time immediacy for a huge gain in speed and system stability.
That's brilliant. Okay, to round things out, one last technical bit. Access methods. The source compares sequential versus random access.
This is basically the difference between a scroll and a book.
A scroll being sequential.
A scroll is sequential access. If you want to read the 500th sentence on a scroll, you have no choice but to physically unroll the first 499 sentences to get there.
And that's what we use for those control break reports.
Exactly, or the batch processing. In any case where you know you need to process every single record in order, just reading from start to finish is the most efficient way.
But I don't want the server to scroll through millions of users to find my account when I try to log in.
And that's where random access or direct access comes in. That's the book. If I say turn to page 300, You don't read pages 1 through 299. You just open it directly.
How does the computer know where page 300 is on the disk?
It uses math, things like index files or hashing algorithms. It takes your user ID, runs a quick calculation on it, and that calculation points it to the exact physical address on the disk where your record is stored. It jumps straight there.
So sequential is for I need everything, and random is for I need one specific thing right now.
That's the perfect rule of thumb. Neither is better. They're just different tools for different jobs.
You know, looking back at all of this, the hierarchy, the buffers, the merge logic, it's so clear that file handling is not just about storage.
No.
It's about maintaining order in the face of chaos.
It is. We call it digital memory at the start, and that still fits. But memory needs structure. If you just threw all your memories into a big pile, you'd never be able to recall anything specific. You need rules.
You need to know if it's text or binary. You need to close the file drawers.
You need logs to remember the sequence of lanes. It's all about creating a reliable system out of unreliable parts.
And what really strikes me looking at the code examples in the sources is just how similar the logic is across totally different languages.
That's the real takeaway here.
The syntax is different, curly braces here, indentation there, but the thinking behind the merge algorithm or the control break, it's identical in Python, Java, and C++.
Absolutely. Languages are just tools. Frameworks come and go every few years. But the fundamental logic of data management, how you sort, how you merge, how you report, that is timeless computer science. If you understand it in one language, you understand the core concept everywhere.
So the next time you hit save or check your bank balance, maybe just take a second to think about all that invisible machinery whirring away in the background.
Buffers flushing, the transaction logs growing.
And those two little digital fingers just zigzagging through the data to keep everything perfectly in order. It makes the virtual world feel a little more physical, doesn't it?
It really does. It's a lot of work just to remember something.
Well, thanks for helping us unpack the archive today. This was fascinating.
My pleasure. It's always great to get back to the fundamentals.
And thank you for listening to The Deep Dive. Keep your files closed, your buffers flushed, and we'll catch you on the next one.